any given model type, so whether it's a line or transform, they have what's known as a minimal set. The minimal set is the smallest number of samples from which the model can be computed. So for a line, how many points is that? Well, 2, all right? But what about transforms, when we're transforming one image to the next, okay? Image transforms are just models. So what is the minimal set of our different transforms? Well, first of all, what are we sampling from? Well, we're sampling from proposed matches, corresponding pairs of points, okay? So suppose I think that one image is just translated of another image. So the transformation is a translation. How many pairs do I need? 1, because if you tell me where this point A is in this other image, I now know the translational shift between any 2 points. Another way of thinking about that is I need a delta x and a delta y, and you give me an x and a y match. So I know what delta x is. I do this complicated thing called subtract, and I do it on y, and that's my offset. Okay. Homographies. Ooh, we talked about this. How many pairs of corresponding points do we need to compute a homography? Do you remember? Paying attention out there? 4. Megan, get it right. How about a fundamental matrix? We showed you something called the 8-point algorithm, right? That said if you had 8 points, corresponding pairs, you can compute that. By the way, it's actually 7. We didn't really talk too much about that. Do you remember when with 8 points we could solve for the fundamental matrix, but then you would sometimes end up with a rank 3 fundamental matrix, so you had to reduce it down to a rank 2. So we did that whole getting rid of the smallest eigenvalue. That's because there's actually fewer degrees of freedom. So in principle, you can do it with 7 points, but we're just going to think of it as 8 points. So the idea is, for a translation, I need 1 pair. For a tomography, I need 4 pairs. For a fundamental matrix, I need 7 or 8 pairs. This is the minimal set that it takes to compute these things. Then you can write down the general RANSAC algorithm. Randomly select, it says S points, or point pair, S elements of a sample set. So you form a sample by pulling out S things that you need. You instantiate your model, so you either draw your line or compute your homography, whatever it is you do. And then you get a consensus set, C sub I. And these are the points that are sort of within the error bound. So if you think of it as homography, homography maps this image to that image. And I can see, are the points that are all these points mapped, how many of the proposed matches now land in the same place that they said they came from? That's the number of inliers. And in fact, you might even terminate this algorithm as soon as that consensus set is big enough. Or you might just repeat it for n times, and then you return whichever model gave you the biggest set. So that's the general RANSAC algorithm. And of course, like any other algorithm, there are some parameters to be chosen in order to make this thing work. So the first parameter is this number S, the minimal set. That's how big is the minimal set. That number is actually usually set by whatever model you're using, right? So if you're fitting lines, that number is 2. If you're doing homographies, that number is 4 pairs. So that's set by the model. A little more problematic was this distance threshold T, or delta as I wrote in the Greek, of saying how far away from the model that you're computing is acceptable to be an inlier. So let's look at that one just a little bit.